Hello, welcome to Lecture 5 of the online course on Explainable Machine Learning and Artificial Intelligence. This is the second lecture in a series of 2 on inherently interpretable models. In the previous lecture, we focused on linear regression, one of the most fundamental and general interpretable models. We used linear regression to introduce some of the fundamental concepts in explainable machine learning. In particular, the concept of feature importance and the concept of trade-off between interpretability and prediction performance. Today, we will move to another set of interpretable models: linear classifiers, trees, and rules. And we will extend to these models the concepts developed in the context of linear regression. This course assumes that you are already familiar with the basics of these models. Here, we will focus on interpretability. The specific goals of this lecture will be to briefly review the class of linear classifier models, and in particular logistic regression, on which we will focus on much of this lecture. Then we will link logistic regression with a previous lecture on interpreting linear regression, and articulate the concepts of feature importance and sparsity for logistic regression. We will describe the geometric and neural interpretations of logistic regression, and we will discuss extensions of logistic regression to models such as score sheets and generalized linear models, and discuss their interpretability. Finally, we will briefly outline 2 other classes of models, regression trees and rule lists, and we will discuss their relation to interpretability. So let's get started with linear classification. First, a quick reminder on what is classification. In Lecture 3 on the general framework, we defined 2 classes of problems. Problems in which the output is continuous, and we call those problems regression problems, and problems in which the output is discrete, and we call those classification problems. Today, we will be focusing on classification. We've considered situations in which the model maps inputs onto an output y that takes values in a discrete set of capital K values, which we call y1 to yk. And each of these output values defines a class. This implies that the model effectively divides the input space into separate regions that correspond to different output values. Linear classification methods correspond to models in which the boundaries between those regions are linear. Let's illustrate this on a couple of simple cases. The simplest case is the situation where we have 2 input features and 2 output values, y1 and y2. The input, or feature space, is then 2-dimensional, and it is divided in 2 regions that correspond to the 2 different values of the output. For a linear classifier, the boundary is a straight line, and it is defined by a vector orthogonal to it. We will call this vector beta, as we did for linear regression. So here we have a situation that is directly related to the geometric interpretation that we discussed for linear regression. Let's now move to a slightly more complex case, where we still have 2 input features, but now 3 output classes. Each output class defines a region in the input space. So we now have 3 regions, and if the classifier is linear, the boundaries between regions are straight lines. So each of the boundaries is now defined by a vector beta that corresponds to a class. A third situation is that we can have more than 2 input features, in general p features, so that the input space is p-dimensional. If we have 2 output classes, a linear classifier splits the p-dimensional space in 2 by a hyperplane. What is a hyperplane? For 3 input features, the hyperplane would be a usual 2-dimensional plane. For p input features, it's a p-1 dimensional plane. In general, a hyperplane in p dimensions is defined by a p-dimensional vector orthogonal to it, and again we will call this vector beta, as in the case of linear regression. Of course, if we have more than two classes, we will have more hyperplanes and therefore more vectors beta. This is the general geometric interpretation of linear classifiers. Let's now go a little more into the technical details. In general, for linear classifiers, the output is encoded using one-hot encoding. That means that the output is a vector of binary variables, zeros or ones, and at most one of the variables is non-zero. In general, for capital K classes, this will be a capital K minus 1 dimensional vector, where the last kth class is obtained if all the variables are 0. In a linear classifier, the output is obtained by first computing a set of capital K minus 1 linear functions of the inputs. This is done for each output class, except for the last one that corresponds to capital K. So we have basically a set of capital K minus 1 linear regressions with coefficients indicated with a superscript small k. Then for each output class, we apply a nonlinear monotonic function g on the linear function fk to obtain either a discriminant delta k or a probability pk. The difference between a discriminant and a probability is that the probabilities are positive numbers that are normalized to sum to 1 over all classes. Finally, the output is obtained as the output with maximal discriminant probability. This is a description of the general class of linear classification models. In this course, we will focus on one specific model, logistic regression, which corresponds to a specific nonlinear function called the logistic function. So let's define the logistic regression in the case of capital K classes. The first step is to compute a linear function f sub k of inputs for each of the first capital K minus 1 outputs. The obtained f sub k values are called class logits. The second step is to compute class probabilities for each of the classes. For the first capital K minus 1 classes, we apply an exponential to f sub k, and then for normalization purposes, we divide by 1 plus the sum of L from 1 to capital K minus 1 of exponential of FL. For the last class, the capital K class, the probability is simply 1 over the normalization factor. This ensures that the probabilities of the capital K classes sum to 1. Altogether, this transformation from the f sub k values to the output is called a softmax. The third and final step is to select the class with maximal probability as an output. This was the general case with capital K output classes. We will mostly be working with two output classes, and in that case, the notations become simpler. For two output classes, we have a single output y that is either 0 or 1. And we have a single linear function f of x, so a single set of coefficients beta. Then the probability that y is 0 is simply exponential of f of x divided by 1 plus exponential, while the probability that y is 1 is 1 over 1 plus exponential. Clearly, p0 and p1 sum to 1, so we can compute only p1 and check whether it's larger or smaller than 1/2. So in linear regression with two classes, usually only p1 is computed, and it can be written as g of f of x, where g is called the logistic function. So in summary, for two classes, logistic regression consists of first applying a linear regression to the inputs with a vector of coefficients beta, and then applying a monotonic nonlinear function g, which is called the logistic function. The result is the probability that the output is 1, so if it's larger than 1/2, logistic regression will output 1, otherwise it will output 0. To make this last step easier, inverting the logistic function, we can rewrite this expression to show that the linear function gives what is called log odds of the output, which is log of p1 over 1 minus p1. So the logistic regression is really a linear regression that outputs the log odds for the categorical output. Altogether, this makes clear that logistic regression is very directly related to the linear regression. So to interpret the outputs of logistic regression, we can use exactly the same concepts as for linear regression. More specifically, each term in the linear part quantifies the contribution of each feature to the probability that the outcome is class 1. So if we want a global explanation for the output of the model, we can directly look at the weights beta in the model, which quantify the importance of different features. If we want a local explanation of the output for a specific input instance, we can look at what we call the effects, where the effect of feature I in instance j is the coefficient beta I of feature I multiplied by the value xij of the feature I in instance j. Then we can apply to logistic regression the same criteria for explanations as we did for linear regression. First, are the explanations social? This point depends on whether the features used by the model are directly interpretable and meaningful for the audience. Are explanations contrastive? As in linear regression, a natural point of comparison in logistic regression is an instance where all the features are 0. For continuous features, this point of comparison is meaningful if the data was mean-centered, because in that case, the instance with all features 0 is precisely the mean of the dataset. For categorical features, using a 0-1 hot encoding for inputs makes models particularly contrastive, as we can compare the outputs when adding or removing inputs. Finally, are explanations short and selective? As for linear regression, this depends on the number of features with non-zero coefficients in the model. If many features have large non-zero coefficients, then it becomes difficult to mentally keep track of the contributions of all the features. So, as for linear regression, one way to make logistic regression more interpretable is to minimize the number of features with non-zero coefficients. Or inversely, have many features with 0 coefficients, and this is called the sparse logistic regression. So the interpretability of logistic regression can be optimized by optimizing sparsity. And this can be done during training in a manner very similar to linear regression. But first, how do we train a classical logistic regression model on data? Because we're looking at classification rather than regression, the most common loss function is what is called the log likelihood. For each point in the training data, we have an input xi and a categorical output yi. The log likelihood of that point under the model is the log of the probability of observing the output yi given the input xi and the model parameters beta. The goal of the training is to find parameters beta that maximize the sum of log likelihoods over the training set. So this is classical logistic regression. To optimize interpretability in sparse logistic regression, the goal is to, moreover, minimize the number of non-zero coefficients. And as for linear regression, an efficient way of doing this is to add what is called an L1 penalty. So instead of maximizing log likelihood, sparse linear regression maximizes a loss function that consists of the log likelihood together with an additional regularizer, the L1 penalty, which penalizes solutions where many coefficients beta take large values. And as for linear regression, these regularizers can be interpreted as a measure of model complexity, so that this loss function effectively implements a trade-off between prediction accuracy and model complexity, or conversely, interpretability. So we'll recover here this concept of predictability-interpretability trade-off that we previously discussed in the context of linear regression. Sparse logistic regression models are a set of highly interpretable models for classification. They become in fact even more interpretable if the inputs are categorical, binary, coded in terms of zeros and ones. Then for each input instance, each input feature is either present or absent. The logistic regression assigns to every feature a score if it's present, and summing these scores then gives a probability for the outcome that can be compared against the threshold. Let's look at a specific example. In a study published in 2016 by Uston et al., the goal was to predict the risk of obstructive sleep apnea for patients. The study in particular developed a classifier based on logistic regression, and this model is summarized in this table. The input features are listed in the left column. They consist of medical history components such as age, hypertension, body mass index, and gender. Each feature was binary, either 0 or 1. In particular, age and body mass index were discretized and turned into binary variables. Each of these binary features was assigned a score, listed here in the right column. And the features were listed by decreasing values of the score. These scores directly correspond to coefficients beta in the logistic regression model. So when a feature is present, the corresponding score is added to the total. The final total is then directly the output of the regression, which specifies the log odds that the patient has obstructive sleep disorder. This total value is then compared to a threshold, in this case 0.19, and if the total is larger than the threshold, the diagnostic is that the patient has OSA. This example directly illustrates why sparse logistic regression is a highly interpretable model. A doctor can directly see how much each feature contributes to the diagnostic, and the doctor can therefore directly internally simulate the model by adding the scores. Here, there is still some mental effort involved in computing the sum of the scores. The model would be even more transparent if the points were simple integers. The study by Uston et al. Actually optimized a version of the classifier in which the points are integers and the threshold is an integer too. The authors showed that this model was essentially as predictive as the previous model with more complex scores. This model with integer scores is very highly interpretable because it has very few features, and it is very easy to see how input features lead to the output. This type of model is called a score sheet. Score sheets are an extension of logistic regression in which the number of non-zero coefficients is minimized, as in sparse logistic regression, but moreover the input variables are categorical and binary, and the coefficients are small integers. Training and optimizing this kind of models is actually quite complex, and this is a topic of current research summarized in an article published by Rudin and colleagues in 2022. So, sparse logistic regression is a key model for classification because it is potentially interpretable and can be extended to be even more interpretable by adding constraints on the coefficients. One such extension are score sheet models that I have just illustrated. Another extension are so-called generalized additive models. What are generalized additive models? Remember that in logistic regression, the log odds of the output are obtained as a sum of linear functions of individual features. Generalized additive models are an extension where the log odds are still a sum of functions of individual features, but these functions can now be nonlinear. The goal of such an extension is to have models with higher predictive performance or expressivity, but which is still potentially highly interpretable, in particular if they are sparse, meaning that they use a small number of features, and if they're monotonic. Here, monotonicity means that the individual nonlinear functions are monotonic functions of individual features, which makes their effects more transparent. Optimizing interpretability in generalized linear model therefore means optimizing both sparsity and monotonicity, and more broadly, the simplicity of the model. How exactly to do this efficiently is a topic of current research. To compare logistic regression and generalized additive models, let's look at an example that we discussed in earlier lectures: intensive care management. As a reminder, here we're considering a situation where a patient comes to the emergency room of a hospital, and the goal is to determine the risk of death from pneumonia based on the patient's data and medical history. The table on the left lists a subset of input features available in the dataset. This is a classification problem, and a study by Caruana and colleagues compared the performance of different models trained on this task. The results are listed in the table on the right. Caruana and colleagues started with classical logistic regression and then examined generalized additive models, as well as generalized additive models with quadratic terms. Then they also considered more complex, non-interpretable black box models, in particular random forest and logit boost. The results showed that generalized additive models, also called GAMs, have a higher predictive performance than logistic regression. Non-interpretable models also have a somewhat higher performance than logistic regression, but their performance is lower than generalized additive models. So generalized additive models have a high performance and are at the same time interpretable. How can we interpret the trained generalized additive models? For each feature in the input data, the GAM fits a nonlinear function, which can be shown graphically. This figure shows a set of GAM terms for a subset of features in the data, such as age, asthma, blood urea nitrogen, the presence of cancer, and so on. Each term in the GAM is a nonlinear function of the input feature. For continuous features such as age, it is a continuous function, and here the results showed that the risk of pneumonia depends on age, respiration rate, temperature, and so on. Note that here these functions were not constrained to be monotonic, which somewhat increases the complexity of the model and limits interpretability. For discrete features such as asthma, cancer, and the presence of other diseases, the nonlinear function is a step function. So once the model is trained, an expert can inspect the set of functions of individual features, check the model, and potentially correct if needed. In this example, we can see in the second panel in the top row that in the model, the presence of asthma appears to decrease the risk of pneumonia, which does not make sense. A similar issue is present with chronic lung disease. As we discussed in the very first lecture, this is a consequence of bias in the training data, because previous patients with such medical history were directly sent to intensive care. Having an interpretable model allows experts to directly spot such issues and correct the model, for example, by removing the corresponding terms. To finish this part on logistic regression, I want to cover two additional methods for interpretation that we discussed for linear regression: the geometric and neural interpretations. We already discussed the geometric interpretation at the beginning of this lecture, so I'll just quickly recapitulate it for logistic regression with two output classes. As we saw, the log odds of class 1 are given by a linear function of input features. As for linear regression, this linear function can be written as a scalar product between two vectors, the vector beta of regression coefficients and the vector x of input features. This directly leads to a geometrical interpretation in feature space, where each axis represents the value of one of the input features. The vector beta defines a direction in this feature space and a hyperplane orthogonal to this direction. This hyperplane corresponds to the set of points on which the scalar product has the same value, and therefore the log odds have the same value. So the vector beta defines a linear boundary that separates the inputs into two output classes. Let's now turn to the neural representation. Again, the first step in logistic regression is just to take a linear function of the inputs. And as for linear regression, this can be simply interpreted as having a neuron that receives features as inputs, multiplies input feature xj by a synaptic weight beta j, and then takes the sum. This is what happens when we have only two output classes. More generally, for k output classes, we will have k-1 linear neurons of this type. And these neurons form a simple linear layer which computes the logits of different classes. The next step is then to apply a softmax to transform these logits into class probabilities, and this can be interpreted as a second nonlinear layer in the neural network. This neural interpretation will be very useful in future lectures when we turn to more general neural network models, because many types of neural network models used for classification could contain precisely this type of nonlinear softmax as the last layer in their architecture. This brings me to the end of this part of the lecture dedicated to linear classifiers and logistic regression. To recap, in this and the previous lecture on inherently interpretable models, we have so far covered linear regression and linear classification. In the rest of this lecture, I will briefly cover two additional classes of models that can be interpretable: decision trees and rule lists. Let's start with decision trees and with a motivation for this class of models. The linear and logistic regression models that we covered so far act on linear combinations of features, and this can make it sometimes difficult to interpret the roles of individual features. In contrast, decision trees are a class of models based on a series of operations on individual features. A second limitation of linear and logistic regression models is that they usually do not include nonlinear interactions between features. Decision trees are one way of addressing this limitation in the sense that they effectively implement piecewise constant prediction functions on combinations of features. More specifically, decision trees are based on two steps. The first step is to partition the feature space recursively into a set of rectangles. The second step is then to fit a simple model on each rectangle, typically just a constant. Let's look at a simple illustration where we have two input features x1 and x2 so that the input feature space forms a square. A decision tree partitions this 2D feature space into a set of rectangles, shown on the left here. It then associates an output value with each of the rectangles, so that the output is piecewise constant. The input-output function implemented by this decision tree is illustrated on the right, where now the z-axis represents the output value, and the output is simply constant in each of the rectangles defined on the left. Why is such a model called a tree? The key point is that the partition in terms of rectangles is defined recursively by a series of split points. Let me illustrate how this partition is obtained. We start from the full feature space, which in this example is a square. The first step is obtained by splitting the features x1 according to a split point t1. This defines two cases. One case when x1 is smaller than t1, and a second case when x1 is larger than t1. These two cases correspond to two subregions of the feature space illustrated on the left. If x1 is smaller than t1, then the next step is to compare x2 to a split point t2. And this defines two subcases that correspond to regions R1 and R2 of our final partition. If x1 is larger than t1, then the next step is to compare x1 to a third split point t3, which defines two additional subregions. And if x1 is smaller than t3, this defines the region R3 in our final partition. If x1 is larger than t3, then there's one more step where we compare x2 to a split point t4, and this defines the final two regions R4 and R5 in our partition. This was a simple example to illustrate the relationship between recursive rectangular partitions and tree models. This example can be directly extended to rectangular partitions in higher dimensions. Training a decision tree model then amounts to finding an optimal rectangular partition according to a given cost function, for example, mean square error, in which case the decision tree is called a regression tree. Let's now turn to interpretability. In which sense are decision tree models interpretable? Well, a decision tree gives us directly the full sequence of steps that lead from the inputs to the outputs, and show in a simple and transparent way how each feature leads to the next step in the decision process. So a decision tree gives us, in a sense, the full causal explanation for how the model produces the decision. However, if the decision tree is very deep, and the same feature occurs multiple times, this full causal explanation can become overwhelmingly complex. So, decision trees are interpretable models only if they are sufficiently shallow and act on a small number of variables. To finish this part on decision trees, let's look at a concrete application. Let's go back to one of the examples we covered in the very first lecture: machine learning for crime prediction. Here, the goal is to predict the risk of rearrest following the release from prison, based on the criminal history of an inmate. In the first lecture, I told you that the US crime system uses a commercial black box algorithm for this. This algorithm takes as an input a large list of features, illustrated on the left here. A study by Zhang and collaborators sought to instead develop a high-performance but interpretable model for the same task. So Zhang et al. Optimized shallow decision trees for this task, and one of the models they obtained is summarized here. It uses only 4 input features. The first one is the number of prior arrests. And the first split point is 5. So if the number of prior arrests is smaller than 5, the model looks at the age at release from prison. If the age at release is between 18 and 24, the model predicts a high risk of rearrest, otherwise it predicts a low risk. If the number of prior arrests is larger than 5, then there's a second branch in the model, shown on the right. In that branch, the model looks at whether the age at release is more or less than 40. If it's more than 40, the model predicts high risk of rearrest. If the age at release is lower than 40, then the model looks at prior arrests for misdemeanor. If the inmate was not previously arrested for misdemeanor, the model predicts low risk. Otherwise, it predicts high risk of rearrest. So this is a very simple and highly transparent model, and strikingly, it has a very good performance with a true positive rate of 80%. Let me finally turn very briefly to rule lists, a class of models closely related to decision trees, and the last in the list of interpretable models we will be covering. Rule lists consist of a series of if-then statements. The if statements define a partition of the feature space in a manner very similar to decision trees. The then statements define the predicted outcomes in each of the partitions. The main difference with decision trees is that rule lists focus on discrete, categorical input features and outcomes. Similarly to decision trees, rule lists are interpretable if they are shallow and act on a small number of features. For concreteness, let's look again at the same example as for decision trees, the criminal prediction task that we have just discussed. The study by Rudin and colleagues optimized a minimal rule list model for this task, and this model is summarized here. If the age of the inmate is between 8 and 20 and they are male, the model predicts high risk of arrest. If not, then if the age is between 21 and 23 and the inmate has 2 to 3 prior offenses, the model predicts high risk of arrest. If not, then if the inmate has more than 3 prior offenses, the model again predicts a high risk of arrest. In all other cases, the risk is predicted to be low. So this is a very transparent model in which the causal chain of decisions is directly clear. So this is a highly interpretable model. Strikingly, Rudin and colleagues showed that this simple interpretable model is in fact as accurate as the black box proprietary model often used in the US criminal system. This brings me to the end of this lecture and to the end of the series of the 2 lectures on interpretable models. To summarize, a broad range of interpretable models exist, starting from linear regression. Different fields tend to favor different types of models, and it is important to keep in mind that a model is interpretable only if the data features are themselves interpretable. Interpretable means that the prediction process is simple and transparent, but in general, fitting or training interpretable models is not necessarily easy, and for many of these models, the optimization problems underlying training are a very active field of research. To conclude, one of the key concepts that I introduced is the idea of a trade-off between predictive performance and the simplicity of the model. This trade-off comes from the fact that making a model simpler typically leads to additional constraints in the loss function, which then reduce prediction performance. How much the prediction performance is actually reduced by optimizing for interpretability is, however, an empirical question that depends on the problem at hand. Often, very good predictive performance can be reached with simple interpretable models. In other situations, interpretable models might not be predictive enough, and this is the motivation for a second approach to explainability, which starts from highly predictive black box models and then seeks to explain their outputs. This is what is called post hoc explainable machine learning, and we will turn to these methods in the next lecture. See you next time!